Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the vast landscape of mathematical physics, few peaks remain as unconquered and as alluring as the complete understanding of turbulence. The swirling chaos of a river's eddy, the unpredictable plume of smoke from a fire, the violent buffeting of an aircraft wing, all are governed by a single set of differential equations. These are the Navier-Stokes equations, formulated in the early 19th century to describe the motion of viscous fluids. Their form is elegant, their statement concise, yet they conceal a universe of complexity that has resisted the full force of mathematical inquiry for nearly 200 years. The central paradox is this: we can write down the laws of fluid motion with startling precision, but we are frequently powerless to predict their consequences. The equations themselves seem to mock our desire for order, allowing smooth, placid flows to erupt into wild, seemingly random turbulence. The question of how to penetrate this mathematical fortress has defined entire fields of study. Some have approached it through brute computational force, others through physical experiment and statistical approximation. A different path, however, was chosen by a mind forged in the abstract world of functional analysis, a world of infinite-dimensional spaces and the operators that act upon them. This was the path of Ciprian Foias. His life's work presents a compelling narrative of a mathematician who built some of the most sophisticated abstract tools of the 20th century, and then aimed them squarely at one of the most tangible and intractable problems in all of science. To understand his celebrated assault on the Navier-Stokes equations, one must first appreciate the deep foundations he laid decades earlier in a realm of pure mathematics that at first glance appears worlds away from the flow of water or air. Foias began his career in his native Romania, within a mathematical culture of immense depth and rigor. He became a student and later a principal collaborator of the great Hungarian mathematician Navier-Stokes. The intellectual environment they inhabited was dominated by the legacy of David Hilbert and John von Neumann, who had established the theory of Hilbert spaces, infinite-dimensional vector spaces that provide the natural setting for quantum mechanics and Fourier analysis. Within this framework, the study of linear operators, which represent transformations on these spaces, had become a central focus. A particularly beautiful and complete theory existed for a special class known as self-adjoint operators. These operators possessed clean, well-behaved properties, their spectral theory providing a powerful way to decompose them into simpler pieces, much like a prism breaks light into a spectrum of colors. The difficulty, however, was that many operators arising from physical and engineering problems were stubbornly non-self-adjoint. They lacked the elegant symmetries of their self-adjoint cousins, and their behavior was far more mysterious and difficult to analyze. This was a fundamental challenge that Foias and Ciprian confronted. Their response was a profound and beautiful intellectual achievement known as dilation theory. Their work centered on a class of non-self-adjoint operators called contractions, which are operators that shrink or maintain the length of vectors in a Hilbert space. The genesis of their theory was a brilliantly insightful idea. Instead of struggling with the contraction operator in its native space, they sought to view it as a piece of a much larger, simpler object. The core principle of dilation theory is that any contraction operator acting on a Hilbert space can be dilated or extended to a unitary operator acting on a larger, encompassing Hilbert space. A unitary operator is the infinite-dimensional analog of a rotation. It preserves all geometric properties of the space, its angles and distances. These are among the most well-understood and manageable of all operators. The genius of this approach was that the original, difficult contraction could be recovered by simply compressing the simple unitary operator back down to the original, smaller space. This technique was revolutionary and meant that the formidable and well-established tools of harmonic analysis, which had been developed for unitary operators, could now be indirectly applied to the enigmatic class of contractions as a way of understanding a complex object by seeing its shadow cast from a simpler object in a higher dimension. This work was far from a mere technical curiosity. It provided a completely new lens through which to view a vast segment of operator theory. The culmination of their decade-long collaboration was their monumental 1970 monograph, Harmonic Analysis of Operators on Hilbert Space. This book did more than summarize the results. It established a new paradigm. Within its pages, they meticulously developed what became known as the Foias functional calculus. This provided a rigorous method for applying mathematical functions to contraction operators. It created a powerful algebra for these abstract objects, allowing mathematicians to calculate expressions like the square root of an operator or the exponential of an operator, tools that are indispensable for solving differential equations. The book became an instant classic, a foundational text that trained a generation of functional analysts. The influence of this early work was both deep and broad. Foias' own thinking was clearly built upon the bedrock of Hilbert space theory laid by Hilbert and von Neumann, and the early operator theory of his Hungarian predecessor Frigyes. In turn, the structure he and Sokovinagy built became a foundation for others. The American mathematician Donald Sarasin, for instance, saw a deep connection between their theory and the theory of function spaces, leading to Sarasin's celebrated theorem on commutance of turbulent operators. Similarly, Israel Goldberg, a towering figure in operator theory and matrix analysis, recognized that these abstract methods could be powerfully applied to concrete problems in linear systems and control theory, bridging the gap between the purest mathematics and engineering. This work on dilation theory cemented Foias' reputation as a master of abstract analysis. It is a field of breathtaking beauty, yet one that can feel profoundly distant from the physical world. For Foias, however, this intricate machinery was never an end in itself. It was the forging of a weapon. He had spent the first part of his career crafting a mathematical lens of unparalleled power, one capable of bringing complex, infinite-dimensional structures into sharp focus. Now, having honed these tools to perfection, he would turn his attention away from a pristine world of abstract spaces and toward the turbulent, chaotic flow of fluids. The grand challenge of the Navier-Stokes equations awaited, and Ciprian Foias was now uniquely armed to confront it. The intellectual arsenal Ciprian Foias had assembled was formidable, forged in the abstract furnaces of dilation theory. Upon his arrival in the United States and his appointment at Indiana University in 1979, he pivoted his focus toward a problem of legendary difficulty, one that had humbled mathematicians for over a century. The elegant, pristine world of operator algebras would now be deployed against the chaotic, swirling reality of fluid dynamics. He turned his gaze to the Navier-Stokes equations, the set of partial differential equations that govern the motion of viscous fluids. These equations are ubiquitous, describing phenomena from the currents of the ocean and the circulation of the atmosphere to the flow of blood through our arteries. Their practical importance is immense, yet their mathematical soul remains profoundly enigmatic. The core challenge lay in their nonlinearity. While the equations themselves appear compact, their terms describe how the fluid's velocity influences itself, creating feedback loops that can cascade into the bewildering complexity we call turbulence. The central questions were as fundamental as they were stubborn. For a given initial state, does a smooth, physically sensible solution exist for all future time? This is the problem of global regularity. Furthermore, can we characterize the long-term statistical behavior of a turbulent flow, predicting its average properties, even if we are unable to predict its exact state at every instant? The French mathematician Jean Larrey had made a monumental first step in 1934, establishing the existence of what are called weak solutions, mathematical objects that satisfy the equations in an averaged sense but may lack the smoothness of a classical physical solution. Larrey's work was a landmark, proving that the problem was mathematically tractable, but it also revealed the immense depth of the challenge. The path forward required a new perspective. This is precisely what Foias, in a legendary collaboration with the French mathematician Roger Tenem, provided. They instigated a complete paradigm shift in how the problem was viewed. Previous approaches often attempted to follow the trajectory of a single solution through time, an endeavor akin to tracking one specific molecule in a hurricane. Foias and Tenem elevated their viewpoint, drawing inspiration from the statistical theories of turbulence pioneered by Eberhard Hopf. They conceived of the entire state of the fluid at any given moment as a single point in an abstract, infinite-dimensional space. In this framework, the Navier-Stokes equations become a dynamical system describing the evolution of this single point within its vast state space. The question was transformed from one about individual solutions to one about the geometry of the entire solution space. The crowning achievement of this new perspective was the introduction and rigorous development of the concept of a global attractor. This was a revolutionary insight. Foias and Tenem proved that for a large class of dissipative systems, including the two-dimensional Navier-Stokes equations, all solutions, regardless of their initial starting conditions, would eventually enter and remain within a specific, well-defined subset of the state space. This subset, the global attractor, possesses two remarkable properties. First, it is compact, meaning it is bounded and closed. Second, and most astonishingly, it has a finite dimension. This discovery carried a profound implication of the seemingly infinite-dimensional, chaotic dance of a fluid after its initial transience, decay, is ultimately governed by a finite number of degrees of freedom. The long-term behavior of the system, with all its intricate patterns, is fundamentally simple in a deep mathematical sense. The infinite complexity collapses onto a finite-dimensional object. This conceptual breakthrough was accompanied by powerful quantitative tools. Foias developed what became known as the Foias-Prodi estimate, a key technical result that provided a pathway to controlling the solution's behavior. This led directly to the theory of determining modes and determining nodes. This theory demonstrates that the long-term behavior of the full, infinite-dimensional solution is completely determined by the behavior of a finite number of its components. These components could be Fourier modes, which represent the strength of different wave-like patterns in the flow, or they could be the values of the fluid velocity measured at a finite number of specific points in space, the determining nodes. One need only observe the temperature at a few key locations in a room, or the amplitude of a few key frequencies in a turbulent signal, and the entire long-term evolution of the system is locked in. This provided a rigorous mathematical basis for what engineers and physicists had long suspected through experiment and intuition that complex systems are often controlled by a few dominant parameters. The full power and scope of this functional analytic approach were codified in the seminal 1989 book, Navier-Stokes Equations, Theory and Numerical Analysis, co-authored by Foias, Temam, and Peter Constantin, a brilliant former student of Foias who had become a leading figure in his own right. This text became the Bible for a new generation of mathematicians studying fluid dynamics and other nonlinear partial differential equations. Within its pages, they presented a rigorous estimate for the dimension of the global attractor for the two-dimensional Navier-Stokes equations. They demonstrated that this dimension is bounded above by quantity proportional to the Grashof number, a dimensionless parameter that relates the buoyant and viscous forces in a fluid. This result was a triumph. Connecting the abstract dimension of a mathematical object directly to a measurable physical property of the fluid system. The impact of this body of work was immediate and lasting. It laid the foundation for the entire modern mathematical theory of infinite-dimensional dissipative systems. The language of global attractors and determining modes became the standard vocabulary for analyzing chaos and turbulence in contexts or beyond fluid mechanics, from chemical reaction diffusion systems to models in theoretical biology. Foias' intellectual lineage is clear and direct. He profoundly influenced his collaborators and students, particularly Peter Constantin and Idris S. Tidi, who have extended and deepened this research program, carrying the torch of the functional analytic method into the 21st century. Foias and his collaborators had successfully attained the infinite, proving that the enduring dynamics of many complex systems reside on a finite-dimensional stage. Yet, this stage, the global attractor, could itself be a geometrically wild object, often possessing a fractal structure with intricate, self-similar patterns at all scales. While its finite dimensionality was a monumental discovery, its complex geometry posed new challenges for both theoretical understanding and practical computation. A new question arose from this success: could an even simpler structure be found within the attractor? Was it possible that the dynamics were confined to a smooth, finite-dimensional manifold, a kind of smooth surface on which the chaotic evolution could be described by a simple set of ordinary differential equations? The search for this smoother, more regular object, the inertial manifold, would become the next great chapter in the quest to understand complex systems. Foias and his collaborators had successfully attained the infinite, proving that the enduring dynamics of many complex systems reside on a finite-dimensional stage. Yet, this stage, the global attractor, could itself be a geometrically wild object, often possessing a fractal structure with intricate, self-similar patterns at all scales. While its finite dimensionality was a monumental discovery, its complex geometry posed new challenges for both theoretical understanding and practical computation. A new question arose from this success: could an even simpler structure be found within the attractor? Was it possible that the dynamics were confined to a smooth, finite-dimensional manifold, a kind of smooth surface on which the chaotic evolution could be described by a simple set of ordinary differential equations? The search for this smoother, more regular object, the inertial manifold, would become the next great chapter in the quest to understand complex systems. This intellectual pursuit was motivated by a deep practical and theoretical need. The center manifold theory, a powerful existing tool, offered a way to reduce dynamics near a specific equilibrium point, providing a valuable local picture of the system's behavior. The ambition of Foias, alongside his steadfast collaborators Roger Temam and George R. Sell, was to find a global counterpart. They sought a single, finite-dimensional structure that would capture the entire long-term behavior of the system, simplifying it completely. Their goal was to find a mathematical object that was finite-dimensional, smooth, and possessed two critical properties. First, it had to be positively invariant, meaning any trajectory that starts on the manifold stays on it forever. Second, it needed to be exponentially attracting, pulling all other trajectories in the state space towards it at an exponential rate. If such an object, an inertial manifold, could be proven to exist, the consequences would be profound. The original, infinitely complex partial differential equation describing the system would become equivalent to a finite system of ordinary differential equations on this manifold. This simplified system is what they termed an inertial form. All long-term dynamics, all the chaos and complexity, would be perfectly captured by this much simpler, finite system. The infinite-dimensional problem would be truly conquered, reduced to a system that could be analyzed and simulated with far greater ease and accuracy. The intellectual breakthrough came with the identification of the precise mathematical condition required for an inertial manifold's existence. In their landmark 1988 paper titled Inertial Manifolds for Nonlinear Evolutionary Equations, published in the prestigious Journal of Differential Equations, Foias, Cell, and TEM laid out the complete theoretical framework. The keystone of their theory is the spectral gap condition. This condition relates to the properties of the linear part of the governing partial differential equation. When one examines the spectrum of this linear operator, which corresponds to the set of its eigenvalues, the condition demands that these eigenvalues must be spaced apart in a particular way. There must be a sufficiently large gap in the spectrum separating the first few eigenvalues, which govern the slow, dominant dynamics, from the rest, which govern the fast, decaying modes. This gap ensures that the slow and fast dynamics can be cleanly decoupled, allowing the fast modes to be expressed as a function of the slow ones, thereby defining the smooth manifold. The theory provided a powerful new lens through which to view distributive systems. Its immediate impact was to provide a rigorous mathematical justification for a practice long used by engineers and physicists, low-dimensional modeling. For decades, scientists had used Galerkin methods, projecting the complex equations onto a small number of basis functions, effectively assuming the dynamics were low-dimensional. The theory of inertial manifolds provided the theoretical bedrock for why such approximations work so well for certain systems. It demonstrated that this reduction was a reflection of a deep underlying mathematical structure. The theory found immediate and spectacular success when applied to several important models in mathematical physics. For the Kuramoto-Sivashinsky equation, a model for flame front propagation and thin film dynamics, and the Klein-Hilliter equation, which describes phase separation in binary alloys, the existence of an inertial manifold was rigorously proven. For these systems, the theory transformed their analysis, allowing for a complete and elegant description of their long-term behavior through a finite set of ordinary differential equations. This was a triumph of mathematical reductionism. Of course, the ultimate prize remained the three-dimensional Navier-Stokes equations, the very problem that had initiated so much of this research. Here, the theory met its greatest challenge. Proving the existence of an inertial manifold for the three-dimensional Navier-Stokes equations requires verifying the spectral gap condition, a task that has proven immensely difficult. To this day, the existence of an inertial manifold for this foundational problem of fluid dynamics remains a formidable open problem, a testament to the profound complexity lurking within turbulent flows. The absence of a proof leaves open the tantalizing possibility that the dynamics of three-dimensional turbulence are intrinsically more complex, perhaps involving interactions across an infinite range of scales in a way that resists this elegant form of simplification. The influence of this body of work radiated throughout the mathematical community. It directly shaped the research trajectory of Foias' own students and intellectual descendants. Navier-Stokes, a prominent student of Foias, went on to make significant contributions by extending and refining the theory, exploring related concepts like determining nodes and feedback control based on these finite-dimensional reductions. Other leading mathematicians, including Michael Jolly and Igor Kikavikar, built upon these foundations, using the concept of the inertial manifold to develop new computational algorithms and to probe the fine structure of solutions to other challenging partial differential equations. The theory became a central pillar in the modern study of infinite-dimensional dynamical systems. This profound success in taming chaos through geometric reduction demonstrated the immense power of abstract operator theory. The conceptual toolkit developed by Foias and his colleagues, forged in the abstract world of functional analysis, had provided a concrete and powerful method for simplifying the most complex physical phenomena. The very same toolkit, designed to find order in the infinite dimensions of fluid flow, would soon find an entirely new application in a world of engineering, circuits, and feedback systems, a domain seemingly far removed from the turbulent eddies of the Navier-Stokes equations. The next stage of his career would showcase his remarkable ability to transport these deep mathematical insights across disciplinary boundaries, with transformative results. The profound success in taming chaos through geometric reduction demonstrated the immense power of abstract operator theory, a conceptual toolkit developed by Foias and his colleagues, forged in the abstract world of functional analysis. It provided a concrete and powerful method for simplifying the most complex physical phenomena. The very same toolkit, designed to find order in the infinite dimensions of fluid flow, would soon find an entirely new application in a world of engineering, circuits, and feedback systems, a domain seemingly far removed from the turbulent eddies of the Navier-Stokes equations. The next stage of his career would showcase his remarkable ability to transport these deep mathematical insights across disciplinary boundaries, with transformative results. This new intellectual frontier was the field of robust control theory. For decades, classical control engineering had made enormous strides by designing systems based on precise mathematical models. A control system for a chemical reactor or an aircraft autopilot was built assuming its dynamics could be captured perfectly by a set of differential equations. This approach yielded controllers that were optimal for the idealized model. The persistent challenge, however, was that real-world systems are messy. An aircraft's aerodynamic properties change with speed and altitude, components wear down, and environmental conditions fluctuate. The idealized mathematical model is always an approximation, leaving a gap between theoretical performance and practical reality. The central engineering problem became one of designing controllers that would remain stable and perform reliably despite this inherent model uncertainty. The goal was to create systems that were robust. The conceptual breakthrough came from a brilliant Canadian control theorist, the late George Ames. He proposed a radical reformulation of the problem. He suggested framing the design of a robust controller as an optimization problem within a specific space of functions. The key was to measure the system's performance by its worst-case behavior. He identified a crucial metric as what is now called the H-infinity norm. In engineering terms, this norm represents the maximum possible amplification or gain from an input disturbance, like a gust of wind hitting an airplane, to a system output, like its deviation from a desired flight path. Minimizing the H-infinity norm of the system meant minimizing this worst-case amplification, thereby guaranteeing stability and performance across a whole range of possible uncertainties. This formulation transformed the engineering challenge into a deep question in complex analysis and functional analysis. It was precisely at this intersection of abstract mathematics and engineering necessity that Ciprian Foias made a pivotal contribution. Collaborating closely with Zanes and with another brilliant mathematician, Alan Tannenbaum, Foias recognized the H-infinity control problem as something familiar, cloaked in the language of engineering. He saw that minimizing this worst-case gain was mathematically equivalent to a classical problem of interpolation, a problem of finding an analytic function with certain properties that fits a given set of data points. This type of problem had a rich history in mathematics, dating back to the work of Rolf Nävenliner and Georg Pick in the early 20th century. The genius of the Foias, Tannenbaum, and Zane's collaboration was to lift this problem into the modern framework of operator theory. They demonstrated that finding the optimal robust controller was identical to solving a problem about operators on a Hilbert space. Specifically, it was a problem of finding the operator with the smallest possible norm that satisfied certain structural constraints, a challenge known as operator interpolation. The abstract machinery Foias had honed over decades, including concepts related to dilations and intertwining operators, provided the perfect set of tools to solve this once intractable engineering puzzle. Their approach offered a complete and rigorous mathematical foundation for the H-infinity method. The power of this new perspective was spectacularly demonstrated in their solution to what is known as the four-block problem. This was a canonical, highly general formulation of the robust control problem that had stumped previous methods. It represented a complex system with multiple inputs and outputs, capturing a wide array of practical scenarios. Using their operator-theoretic methods, Foias and his collaborators provided a complete, elegant, and computable solution. This was a landmark achievement. It provided engineers with a systematic recipe for designing high-performance controllers for complex systems, from sophisticated aerospace vehicles to industrial manufacturing processes. The mathematics guaranteed that a controller designed this way would function reliably, even when the physical system deviated from its textbook model. The impact of this work was both immediate and enduring. It provided the rigorous underpinnings for a revolution in control engineering. The H-infinity methodology became a cornerstone of modern control theory, a standard topic in advanced engineering graduate programs worldwide. The algorithms derived from these operator-theoretic principles are now embedded in commercial software packages, such as the robust control toolbox in MATLAB, used daily by engineers to design systems for satellites, robotics, and power grids. A generation of leading control theorists, including Pramod Karganikar and Keith Glover, built directly upon the foundations laid by Foias and his colleagues, further developing these methods and making them more accessible for engineering practice. This venture into control theory revealed a deeper truth about Foias' work. The mathematical structures he explored were profoundly universal. The same abstract principles that described the geometric structure of fluid turbulence also govern the design of a stable feedback circuit. His contribution was a powerful testament to the idea that translating difficult, concrete problems from science and engineering into the language of operators on Hilbert spaces could unlock their solutions. The solution to the four-block problem, while a monumental achievement in its own right, was itself a specific manifestation of an even more general and powerful mathematical truth. This deep unifying principle, a result known as the commutative lifting theorem, stood as the abstract engine driving many of his most celebrated results, forming the final, unifying thread in the grand tapestry of his intellectual legacy. The intellectual bedrock supporting these diverse accomplishments is the celebrated commute lifting theorem, a result Foias developed in close collaboration with Baylor-Schofield. This theorem stands as a crowning achievement of 20th century operator theory, a piece of profound mathematical machinery that provides the abstract engine for solving a vast array of concrete problems. Its genesis lies in the foundational work on dilation theory pioneered by Schofield, which showed that any contraction operator on a Hilbert space could be viewed as a piece of a larger, more structured unitary operator. The question that naturally followed, pursued by mathematicians like Donald Saracen in the context of interpolation problems, was how relationships between these smaller operators behave when expanded to their larger unitary counterparts. The commute lifting theorem provides the definitive and elegant answer. It addresses a core problem of extension. Imagine two Hilbert spaces, let's call them H and H prime. On each space, we have a contraction operator, meaning an operator that shrinks or preserves the length of vectors. Let us call these operators T is on H and T prime on H prime. Now, suppose there exists another operator, A, which maps vectors from H to H prime and forms a structural link between T and T prime. This link is an intertwining relationship expressed by the equation of times T equals T prime times A. The theorem then poses a powerful question. Since both T and T prime can be dilated to minimal unitary operators, U and U prime, on larger Hilbert spaces, can we find a new operator, B, that preserves the intertwining relationship on this grander stage? That is, can we find a B such that B times U equals U prime times B, and which extends while maintaining its norm? The theorem's resounding affirmation is what gives it such immense power. It confirms the existence of such a lifting and, more importantly, provides a complete characterization of all possible solutions. This result transformed a collection of seemingly disparate challenges in analysis and engineering into manifestations of a single, unified principle. The classical interpolation problems of Navier and Piech, which asked to find an analytic function satisfying certain constraints, were revealed to be questions about operator lifting. The model reduction problems in systems theory, seeking to simplify complex system models while preserving their input-output behavior, found a rigorous foundation within this framework, and, as seen, the formidable four-block problem in H-infinity control theory, which appeared almost intractable from a purely engineering standpoint, yielded to a solution derived directly from the theorem's machinery. The commute lifting theorem provided a universal translator, a Rosetta Stone that connected the language of engineering specifications to the deep grammar of functional analysis. The reception of this theorem within the mathematical community was one of profound appreciation for its depth and utility. It represented a beautiful synthesis of decades of work in operator theory, generalizing earlier, more specific results, and providing a tool of unparalleled scope. Its influence propagated rapidly, becoming a cornerstone for a new generation of operator theorists, including Joseph Ball and Israel Goldberg, who further developed its applications in systems theory and complex analysis. The theorem epitomizes the Foias style in ascent into the highest levels of abstraction, yielding a tool of immense practical consequence. It is a testament to the idea that the most elegant mathematical structures are often the most powerful. Ciprian Foias' intellectual legacy is therefore a grand arc, a journey that charts a course from the most fundamental questions about the structure of infinite-dimensional spaces to the turbulent, chaotic motion of real-world fluids and the intricate logic of feedback control. His work offers a powerful counterargument to any perceived division between pure and applied mathematics. For Foias, this was a false dichotomy. The universe of abstract operators and the physical universe of flows and forces were two dialects of a common language, and his genius lay in his fluency in both. He demonstrated with remarkable consistency that the most challenging, physically motivated problems could be eliminated and frequently solved by translating them into the precise and elegant language of operators on Hilbert spaces. This functional analytic viewpoint is his most enduring contribution. It is a methodology, a way of seeing the world that has reshaped entire fields. In fluid dynamics, his work with Peter Constantin and Edris Tedi on the Navier-Stokes equations provided a new geometric and analytic lens through which to view the problem of turbulence. They established rigorous bounds and identified determining modes and nodes, transforming the field once dominated by physical intuition and numerical simulation into one where the tools of modern analysis could gain a firm foothold. His influence persists directly through the lineage of his many brilliant students and collaborators. Constantin and Tedi, now leading figures in mathematical physics, carry forward this approach, continuing to unravel the mysteries of fluid behavior with the sophisticated tools Foias helped to forge. Similarly, in control theory, his collaboration with Alan Tannenbaum and others on H-infinity methods provided a rigorous mathematical foundation for robust control, solving problems that were critical for aerospace, chemical engineering, and robotics. This work showed engineers that the abstract world of operator theory was a source of powerful, practical solutions. Tannenbaum, in turn, has continued to bridge these worlds, applying geometric and analytic methods to an even wider range of problems in engineering and even medical imaging. The legacy is a living, evolving intellectual tradition passed from mentor to student, a chain of inquiry that ensures the Foias perspective remains vital and generative. His life's work stands as a testament to the power of deep abstraction to solve the world's concrete complexities. He was a mathematician who saw the infinite-dimensional geometry of a Hilbert space in the swirl of a turbulent eddy and the structure of a non-self-adjoint operator in the design of a stable circuit. His contributions were immense, a collection of foundational theorems and groundbreaking papers. Yet, the whole of his impact is greater than the sum of its parts. Ciprian Foias gifted science and mathematics a new way of thinking, a powerful and unified vision that continues to inspire and empower researchers to see the hidden mathematical structures that govern our world. His work remains a powerful reminder that the deepest truths are often found at the intersection of seemingly distant domains of human thought.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.